In this video, we're going to continue our discussion of molecular orbital theory. And we're going to specifically talk about two properties of a molecule that can be determined using molecular orbital theory. And those are the bond order for a molecule and whether a molecule is paramagnetic or diamagnetic. So let's start by talking about the bond order for a molecule. In molecular orbital theory, a bond order is a measure of how strong a covalent bond is between two atoms. Not all covalent bonds are the same, of course. Some are strong, some are weak. The greater the bond order, the stronger the covalent bond is. We can calculate the bond order by drawing a molecular orbital diagram for a molecule, and then counting the number of bonding electrons that molecule has, subtracting from that the number of anti-bonding electrons that molecule has. And then we divide that by 2 in order to get our bond order. If we calculate a bond order of 0, that indicates that molecule is too unstable to exist. So the covalent bond will not form and that molecule cannot exist. So since electrons in bonding molecular orbitals stabilize a molecule and electrons in anti-bonding molecular orbitals destabilize a molecule, the more bonding electrons we have, that will result in a stronger covalent bond. So let's look at a very simple molecule and calculate the bond order. Let's look at H2. So if we look at its molecular orbital diagram for H2, we have the electron configuration for a single hydrogen atom, and here's another single hydrogen atom. When these two atoms form a molecule, we get a bonding 1s orbital and an anti-bonding 1s orbital. The two electrons will go in the lowest energy, that would be the bonding molecular orbital. So this would be the electron configuration for an H2 molecule using molecular orbital theory. Now if we look at this, we have 2 electrons in our bonding orbital, and we have no electrons in an anti-bonding molecular orbital. So we could calculate the bond order by taking the bonding electrons, which we have 2, subtracting from that the number of anti-bonding electrons, which is 0, and dividing that by 2. So of course we would get a bond order of 1. So H2 has a bond order of 1, indicating this has a single bond between the two, and it is a molecule that can form. It doesn't have a bond order of 0. So let's look at our other terms, paramagnetic and diamagnetic. Paramagnetic is defined as a molecule that has at least one unpaired electron. So when we look at its electron configuration using molecular orbital theory, we want to see, does it have any unpaired electrons? If it has at least one unpaired electron, then that molecule is weakly attracted to a magnetic field. So some molecules are actually attracted to magnetic fields, and molecular orbital theory allows us to predict that. Diamagnetic means that all the electrons in those molecular orbitals are paired, so there's no unpaired electrons. Molecules that are diamagnetic are not attracted to magnetic fields. They're weakly repelled to those magnetic fields. So let's look at our simple molecule again, H2, and determine whether it's paramagnetic or diamagnetic. So we looked at its molecular orbital diagram, and we see that we have 2 electrons in the 1s. So those electrons are paired. They're both in the same molecular orbital. We don't have any unpaired electrons. Again, we're only looking at the molecular orbital diagram, not over here for the individual atoms. So for H2, we don't have any unpaired electrons, so that means that H2 is diamagnetic. It is not attracted to a magnetic field. Let's look at a larger molecule. Let's look at N2, and let's calculate the bond order and determine whether nitrogen N2 is paramagnetic or diamagnetic. So first, here are we're just going to look at the valence electrons. We have our two nitrogen atoms, and those are going to bond together to form a nitrogen molecule. So here's the electron configuration, just looking at the valence electrons for nitrogen. And if we combine these atomic orbitals to form our molecular orbitals, we get a sigma 2s, sigma star 2s. And then our 2p orbitals, since we have 6 of those, we get 6 molecular orbitals. Our pi bonding, and then we get a sigma bonding, sigma 2p bonding. And then we have our pi 2p anti-bonding up here, and our sigma anti-bonding 2p molecular orbital. So this is the order of energy that those molecular orbitals will form. And so we start in the bottom, placing our electrons. We have a total of 2, 5, and 5 is 10. So we have a total of 10 electrons that we have to place. So we put them one at a time in the sigma 2s, and then our sigma star 2s, our pi 2p. Again, these are degenerate orbitals, so we put one in each, and then we go back and start pairing up. And then our sigma 2p, pair that up. So that's 2, 4, 6, 8, 10. So that's all 10 electrons. So let's calculate our bond order first. Now we have down here, this is a bonding molecular orbital, and this is an anti-bonding. So I'm just circling the anti-bonding. Both of these are bonding, and then this is also a bonding molecular orbital. So our bonding molecular orbitals, we have 2, 4, 6, 8 bonding electrons and 2 anti-bonding electrons. So we want to plug those into our formula. 8 minus 2, bonding minus anti-bonding, divided by 2 gives us a bond order of 3. So nitrogen is a very, very strong covalent bond, very analogous to a triple bond. And so we can calculate the bond order like this. Now also, as you notice, nitrogen did not have any unpaired electrons. Notice that there are no unpaired electrons, so that means that nitrogen is diamagnetic. So let's look at one more example to calculate a bond order and whether it's paramagnetic or diamagnetic. Let's look at O2. So we have our oxygen, our atomic orbitals. We put our electrons in those. Again, we're just looking at the valence electrons here. Our atomic orbitals will combine to form molecular orbitals. Our 2s will give us a sigma 2s and a sigma star 2s. Now notice that we've got a different order with the pi and the sigma. That was covered in a previous video lecture. So we have our sigma 2p and then our 2 pi 2p molecular orbitals, and then our pi 2p antibonding and sigma 2p antibonding. So now we have 2, 4, 5, 6, and 6 is 12. So we have 12 electrons we have to place. We start in the lowest energy molecular orbital, the bonding, then the antibonding. We put them in our sigma 2p, one in each of our pi 2p's, and then we double up. That's 2, 4, 6, 8, 10, 11, 12. So here we have our electron configuration, our molecular orbital electron configuration for an O2 molecule. Now let's count up our bonding electrons. We have 2 here, and then we have 2 anti-bonding, and then we have our bonding here, and both of these are anti-bonding. So our bonding electrons, we have 2, 4, 6, 8. Our anti-bonding electrons, we have 2, 3, 4. Okay. So 8 minus 4 divided by 2, that's going to give us our bond order. And also notice that here we have 2 unpaired electrons. So that means that O2 is going to be paramagnetic because it has unpaired electrons. So it will be weakly attracted to a magnetic field. So let's calculate that bond order again. We said we had 8 electrons in bonding orbitals. We have 4 in our anti-bonding orbitals. So anti-bonding electrons, we have 4. 4 divided by 2 gives us a bond order of 2, which would be analogous to oxygen having a double bond. So again, a very strong bond, and As we mentioned, it is paramagnetic because we had those two unpaired electrons in our antibonding 2p orbitals. So be sure you can calculate the bond order, determine whether a molecule is paramagnetic or diamagnetic using molecular orbital theory.